Welcome back, ladies and gentlemen. So, we've had some time now to practice a little bit with this idea of something moving at a constant velocity and the idea that we can map out the motion of that object a couple different ways. Remember, we can literally write down in words how this object's moving. We talked about in the previous worksheets how we can read a position time graph or create a position time graph to model the motion of an object. And we've also talked about the idea that we can draw what we refer to as a motion map, which remember is basically that kind of map that every second a little dot is dropped where the object is. Okay, it's kind of like a little radar map of the object moving. All right. Now, today, this worksheet, worksheet 3, is going to introduce another way we can kind of model the motion of an object. All right. And that is by graphing the velocity of the object versus the time it's at. Okay? Now, remember, we talked about the idea first. We have this idea of position time graph, where literally all we're doing is we are graphing the position of the object and the time it's at that position. All right? Well, the velocity time graph is similar in that what it's doing is it is graphing how fast the object is moving at that particular point in time. All right? Now, to kind of talk about it, I'm going to go to a couple different little scenarios to kind of show us how we can kind of visualize this velocity time graph. And then we're going to come back and work on worksheet 3. All right. So what I'm going to do first is I'm going to go to a simulation. So this is in something called PhET. Some of you might have used it in other classes. We're going to use it sometimes in this class, depending on if the simulation works. But what this is I have this individual, this gentleman that is sitting up top. And as you'll notice right now, he is sitting in a running stance. Now what's going to happen is I'm going to hit play. And when I hit play, I am going to let him start moving. Now, the way I have it set up is that he is going to start moving to the right at a constant velocity of 3 meters per second. And I want you to kind of pay attention to the graphs that he creates by the time he gets back to his house. All right, so remember, I have a position time graph, which is something we've seen before. And in fact, I'm going to take it off. And we're just going to literally look at the position graph right now. So I just hit play. And when you know it, that's exactly, and he runs into the wall. I did not realize he was going to do that. Okay, but once you know it, that's exactly what we expected. We see if he's going at a constant velocity, he moves kind of in this nice linear fashion until right here where he ran into the wall. And then, of course, he stopped, so his position stopped changing. All right? But we're just seeing this idea that we can kind of look and visualize this person moving at a constant velocity and see the kind of graph that he creates. So I'm going to clear that. Now, this time I'm going to run the exact same simulation, but now I'm going to set it up so that we can also see how the velocity time graph would look. All right, so remember, this first graph is measuring this guy's position with respect to the time. The second graph is measuring how fast he's going with respect to the time. All right, so let's just hit play and watch. All right. All right, so once again, we see this graph just like we've seen it before. We have the nice constant velocity, so nice linear fashion. If we look at the velocity graph, though, we see something a little bit different. All right, instead of it being a diagonal line like the position graph would be, we notice that it's just some sort of horizontal line. We can zoom in a little bit. And we'll zoom back out. That's not that important. Okay. What we want to see out of this is that when we are going at a constant velocity, what that means is that it's not changing. Okay. No matter what time we're at until this individual runs into the wall, they're moving at the same velocity. So if I'm graphing it on a velocity versus time graph, it should look like just the same velocity as I move forward in time, which is why this line is just a flat horizontal line, because what that signifies is that this object is moving with a constant velocity, it is not changing. And of course, because it's moving with some velocity, it is above zero. In this case, it's about 3 meters per second. All right. Now, of course, when the individual runs into the wall, you'll notice that now the person stops. So the position stops changing, so this becomes horizontal. Excuse me. And the velocity graph changes. And now we have once again a horizontal line, but now because they're not moving, they have a horizontal line at 0. All right, because what we're seeing is that they have a constant velocity of 0. So whenever someone's stopped or at rest, one way you can think about it, if you want to be really specific, is you can say, oh, you're not stopped, If someone's just sitting there and they're saying, "Yeah, I'm stopped, I'm not moving," you say, "You're not stopped. You're just moving with a constant velocity of 0." All right. I'm sure it'll make you very popular. And of course, with all the chemists and biologists in the crowd, they won't understand what's going on because they're too busy focusing on bubbles or squishy things. All right. But for physicists, they'll look at you and say, "I got you," and understand. All right. Now, with that being said, that's kind of just a little example of what this looks like. Another way we can look at it as well is just kind of looking at if I just have a simple graph and I have a position versus time graph that looks like this, nice and linear. The velocity versus time graph is just going to be a horizontal line because it's not changing. All right. Now, we'll remember that to figure out how fast an object is moving, we have to take the slope of the position versus time graph. All right. Well, for the velocity time graph, it's even easier. If I ask you the question, how fast is this object moving? All you have to do is literally read the graph. All right. Now, what's interesting is, let's say that I'm going to draw a velocity time graph. Let's say an object actually moving faster than it was previously. All right. I can change this graph to make it look like that. So the velocity, let's say we had the individual from this one. Let's say we set it to now he was running at 6 meters per second. All right. Well, that would mean that his velocity would increase. So now it would look like this. All right. So it's still constant velocity, but because I've increased it, I've had to basically put it higher on the velocity time graph because I've increased its velocity. And you notice when I did that, it changed the position time graph. It's still linear, but because this individual is now moving faster, it has to have a higher slope to signify it's moving faster. All right? Excuse me. So what we're trying to see on this, ladies and gentlemen, is just the idea that velocity time graphs and position time graphs go hand in hand. And if you are in calculus this year, and if you're not in calculus, don't worry, this is not going to include you. But if you're in calculus this year, at some point you're going to start talking about the idea of position, velocity, acceleration, and the idea of derivatives. And this is exactly where that comes from. All right? Because we're going to find out that all these things are related together. All right? Now, coming back to our actual worksheet, the reason this is going to be important to us is because, once again, we are spending this whole first unit not only talking about the motion of an object, but we're also getting used to a lot of different ways that we're going to start to represent how things move in physics class. All right? So now, I've given you 4 different tools to kind of model the motion of an object. The position time graph, the velocity time graph, a literal written description, and a motion map. All right? Now, your first task is we're going to look at this. We're going to do this one together. And then the second one, we'll kind of, you do a little guided practice, as much guided as you can, remotely. So, for the first one, you'll notice that in each of these scenarios, it's going to give you one of the 4 options. All right, so one of the 4 will be completed, and your task is to fill out the other 4. Well, of the 4 right now, it gave us the position time graph. All right, it didn't tell us anything about the velocity time graph or the motion map or the written description. We're going to have to figure that out ourselves. If we look at this graph, though, this one's going to be pretty simple. All right. If we take a look at this graph, this is a horizontal line, okay? And remember, this graph, we want to, and I'll keep re-emphasizing this, in physics, when we graph stuff, they have physical meaning, all right? It's not just like math class where you just graph x versus y, and it's great, but then you're like, well, who cares? Give me the next problem. This physically means something. So in this case, we look at this object, all right? This object is not moving because you'll notice its position is not changing, all right? It's just stuck at this one position. It's got a negative position, so it's probably behind the origin. And it's sitting there at rest. All right? That means, right away, we know enough that we can do the other 3 parts pretty easily. Now, I'm actually going to do the velocity time graph first, because the velocity time graph for this, and what I'm going to do is I'm going to talk you through the answer, and then I'm going to flip to the master sheet so you can see it. Because the velocity is 0, this velocity time graph is going to be very unique, because not only is it going to be a horizontal line because it's a constant velocity, but it's also going to be at 0 because the object's at rest. All right, so when you draw this, the graph for this one is just going to be literally just a horizontal line that goes this way. And of course, it's going to stop at the same time that this graph stops. All right, now for the written description, remember when we write our description, we want to include a couple things. We want to always include the starting position. We always want to include the way we're moving. and we always want to include the type of motion. All right. Well, of course, looking at this one's pretty simple. We can just say, we can say for the starting point, this object starting in a negative position remains at rest. And that's it. Because it's not, it tells us all we need to know. It's starting in the negative position, it's not moving, so it remains at rest. And that's really it that matters. Okay? And of course, the motion map, what we do is we're going to pick a starting point. Remember, there are no numbers here, so it's not particularly important where you put it on the motion map, except for the fact you need to make sure you're on the negative side of it. Okay? And of course, this is a motion map, so remember, we're putting dots to represent where we are every second. And because this object is not moving, as we talked about in kind of the previous worksheets, what we do is we just draw dot, 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 just vertical dots to represent I'm not changing my position at all. Okay? So when you put that all together for the first one, it should look like this. All right? And of course, and I do apologize for the kind of scribbled look of the writing I have over these graphs, but this is actually something I would like you to include in your graphs as well, just to kind of, little additions so we know. A position time graph tells us where we are. All right? Just by reading it, it tells us where we are. A velocity time graph, just by reading it, tells us how fast we're going and what direction we're going in. All right? Because velocity, remember, can be positive and negative, so that can tell us if I have a graph that shows positive velocity, it tells me I'm going in the positive direction. All right, so right there, the three other answers we talked about. Looks pretty good. Remember, of course, at any point in time, if you're like, Mr. Manny, going too fast, just pause the video and you can write stuff down. Okay, so just whenever you need to, just pause the video. But with that being said, let's go to the next one. All right, so the next group of four. This time, it's given us a velocity time graph. All right, and now what it wants us to do is it wants us to draw a position time graph, a written description, and a motion map for this object. All right. Now, if we look at it, this time we can see the velocity time graph is not 0 anymore. Okay, it has some velocity. And we'll also notice that it's not on the positive side, but it's on the negative side. So right away, this graph tells us a couple things. It tells us, one, how fast we're going. And of course, and it roughly tells us that. It doesn't really tell, it just tells us we have some constant velocity. It also tells us that we are going in the negative direction. But there's one piece it doesn't really tell us. All right? And that piece is, if I look at this graph, is there anything that tells me where this object starts? All right? If you just kind of look at it and think about it, is there anything in this graph, just by reading it, that literally I can say, oh yeah, this is starting here? And the truth is, it doesn't. And that's the one piece about a velocity time graph that's missing. If you read just a straight velocity time graph, what's going to happen is that it will tell you how fast you're going and the direction you're going in. But it's not going to tell you where you start. All right? Because of that, that means when you actually do your written description here, you can have your graph start anywhere on the position axis. Okay? The starting position could be anywhere that you define. Because all that really matters is just that, once again, sometimes we have to pick where we start. Okay? So, with that being said, let's look at this velocity time graph. We clearly said it's got a constant negative velocity. So, I want you to take, I don't know, take about 3.5 minutes, take a stab at this. I want you to try and fill in the three graphs. So the position time graph, the written description, and the motion map. And then, once you think you've got a good idea, come back and we'll talk about the answers. All right? So hopefully you had a chance, ladies and gentlemen, to kind of go through and kind of put down your answers for this part for worksheet 3. So let's look at the position time graph first. And to actually do this, I'm going to go back to this little thing right here. All right. So I have a velocity time graph where the velocity is constant. It's a horizontal line, but it's on the negative side. So I need to move these down. And as I do that, and I'm actually going to move, I do apologize, I'm playing around with this a little bit, but I just want to get this. All right, so it's got now its constant negative velocity. You'll notice that the position time graph has changed, and what it looks like is it looks like something that has basically a constant negative slope, because remember that negative slope means it's got negative velocity, and because it's linear, it's still a constant slope. So your graph is going to look like this. And you'll notice if I can move this wherever on the position axis, and it doesn't do anything to the velocity versus time graph. All right. So remember, the starting position doesn't matter. The starting position is not defined here. So because of that, your position time graph can be anywhere on the position axis as long as it has a constant negative slope. So it needs to be a diagonal line going down and to the right. Okay. Now for the written description, I'm just go kind of shift over to mine. All you need to do is, once again, you define the starting point, and because this does not explicitly say you are the one that gets to pick the starting point, I explicitly said it starts at 3 meters. You don't have to say it. You could just say the buggy starts at a positive position. You could say it starts at a negative position, as long as you define where it starts, and then discuss how it moves with a negative velocity in the negative direction. And actually, this answer is missing something. It needs to say with a constant negative velocity. Okay? And that's a phrase we want to start getting comfortable with, this idea we can, it's just saying positive or constant positive velocity or constant negative velocity. All right? But right there, it's moving at with a constant velocity in the negative direction, and it's doing that because when we look at the velocity time graph, the velocity is not changing, and it's on the negative side. All right? Now, the last piece is the motion map. Once again, wherever you pick your starting point is going to dictate where you start on the motion map. But all you need to do is just draw a motion map that shows something with a constant negative velocity. So because of that, you should have the dots probably moving from right to left, and you should have it so that they are equally spaced apart to represent they're going at a constant velocity. And remember, of course, we need the arrows in there, the vectors, to represent which direction we're moving in. All right? So that's kind of a brief rundown on what these look like, okay? And just kind of how we include the velocity time graph. So let's flip to the next page. All right. The next three are all kind of a little bit more complicated. And once again, what I want you to do, please, is you're going to kind of work through, and this is a great thing if you're working on this remotely, either talk to someone who's been in class or work in someone else who's working remotely. Once again, I want to keep emphasizing, I know this is remote education, and this can be frustrating sometimes. Keep looking for partners to work with, okay? So my best suggestion is to find someone else to work through these questions with. Once again, what we're going to do is we are going to I'm going to let y'all work through them, and then we'll talk about the answers. All right? So with that being said, I want you, if you could please, ladies and gentlemen, I want you to work on this third. This will be question 3. All right? It gives you the written description and nothing else. And it does talk about the idea. It says close to the motion detector. All right? We're going to start using a motion detector the next couple of days. So you can just assume the motion detector means origin in this case. All right? So take as much time as you need to get through this first question. When you think you have a pretty good answer, unpause the video, and let's see it. All right, so hopefully, ladies and gentlemen, you had a chance to kind of work through question 3. So it starts with a written description. The object starts close to the motion detector, which we're going to define as the origin. It moves at a constant, moderate speed in the forward direction for several seconds. Forward direction is just a fancy way of saying positive direction. Then it stops for a few seconds before returning to its starting point, once again at a moderate speed. All right? So what we're going to see, and this is a question I didn't really explicitly say how you did the velocity graph. It was changing. I just want to kind of, I'm hoping to see what you'd be willing to experiment with, is that when we draw this, I usually want to start with the position time graph because to me that makes it easier. So I'm going to have my object start close to the origin. It's going to move with a constant moderate speed in the forward or positive direction. So what I'm going to do is I'm drawing just a diagonal line that's moving in the positive direction, just like I have. Then it stops for a few seconds. And we know when we're drawing a position time graph, when something stops, we draw just a horizontal line at that position to signify this position is not changing. And then it turns around, it says return to a starting point. So it turns around once again at a moderate speed. So what it does is it's now going in the negative direction, but the number or the steepness of the slope is still the same. All right? It's just now going in the negative direction. Now, because of that, if we move down to the velocity time graph, what you're going to do, and we're going to find out, is that there's actually, well, the little missing piece right here. We're going to talk about in the next unit what that actually looks like. But what you do is just basically every section, you just draw the velocity time graph line for that section. All right, and it is going to look ugly at first. It's a weird little piecewise function. So for the first section, it's got a constant positive velocity, so it needs to be a horizontal line on the positive side of the velocity axis. Then it stops. So we just drop down, whoop, magic, and we stop for a few seconds. So once again, horizontal line, but it's 0. And then for the third and final piece, this time it's now going in the negative direction. So it once again needs to be a horizontal line. It has velocity, so it's got not 0, but it's on the negative side because it's going backwards. All right. So what you're going to see is that for stuff like this, it just kind of, you just once again break it up into little sections like normal, and then just kind of pick each section and draw the velocity graph that matches that section. All right. Then, of course, for the last piece, for the motion map, we start close to the origin or at the origin. It's really up to you. We have the dots kind of spaced together to signify it's going at a constant velocity. Then it stops for a couple seconds. That's why the dots are now stacked on top of each other. And then the dots start to return back to where they came, so they now are going in the negative direction. But once again, we try our best to keep the spacing the same. I must have freehanded this because the spacing's not great. Remember, you have a ruler. Use it. If nothing else, by the time we leave this class, we will have immaculate drawings that will be worthy of artwork. All right? So, right there, that's question 3. So, if you could, please, I want you to jump down, and I want you to do questions 4 and 5. You know what? Do both of them. Play around a little bit, experiment, see kind of what happens, and then once you think you have a good idea, I'll talk about the last 2. Okay? But we're doing great. We're almost done. Y'all are doing awesome. Keep rocking and rolling. All right, so hopefully you got a chance to work through 3 and 4. Okay, so we're gonna work, or excuse me, 4 and 5. So we're gonna look at number 4 first. So this time, once again, it gave us a velocity time graph. All right, excuse me, give us a position time graph. I'm getting all my graphs mixed up. So when you have a position time graph, remember you can pick really any of the 4 things to start with. All right. Let's start with the written description. Sometimes I find that to be the easiest, especially when we're not really comfortable, if we're not comfortable with graphs to start with. Writing out what's happening is awesome because then in your head you already know what's going to happen, so it makes it easier to kind of lay out the graph. So in this case, we have a position time graph. We want to know a couple things in the written description. First, the starting point. Well, looking at this graph, the starting point is on the negative, it has a negative position. So we could say this object starts behind the origin, or starts at a negative position, and it moves with a constant positive velocity. All right, because if we look at it, even though it's on the negative side, this is something that's going to be confusing because we talk with positive and negative. Remember, positive and negative in this class does not mean greater or less. All that means is the direction. So what this graph is saying is basically this person is starting behind the origin, all right, and they are taking off and moving towards the origin, and then they run past the origin, all right. So for the written description, we say it starts in the negative position. It moves with a constant positive velocity. Then, in the second half, we notice that the object now is not moving with a positive velocity. They're not moving with a negative constant velocity. All right? And the other key piece here that's important is that you'll notice this slope is much steeper than this slope. So for the second piece, we now say this object, then the object moves with a constant negative velocity that is slower than the first. Or you can just say a slower constant negative velocity. It's really up to you, as long as you signify that the second section is going slower than the first section. All right? The velocity time graph. Remember, once again, we talked about this idea that if you have a graph like this, just break it up into sections. Velocity time graph is no different. Break it up into the sections. So section 1, clearly this has a positive constant velocity, so we need to draw a velocity time graph that shows that. So positive would be on the positive side, and it's pretty fast, so it's going to be higher up on the graph to show that, so something like that. Okay, and that line, of course, only goes as far as this line does on the time axis, and then once it changes, now we have a constant negative velocity that's slower, so we need to have it on the negative side. It needs to be horizontal because it's constant, but it needs to be closer to this. And it really, what I mean is it needs to be closer to 0 because it's not as fast as it was before. So now maybe it's like here. All right? So we have something like this. All right. Now, there's one catch with this graph. And actually, I messed this up. I'm going to scribble this out for a reason. That's the written description we talked about it. That's the velocity time graph. The motion map. This is one of the few pieces where a motion map actually kind of gets messed up a little bit. Because this object never really stops, all right? It just turns around on a dime and starts going the other way, but it never actually stops for any point in time. What happens is that when we do our motion map, remember, we're doing like dots. So it would be like my position here would be right here. My position when I got to like here would be here. My position when I got here would be here. And then the next second, if this was 1 second, 2 seconds, 3 seconds, 4 seconds, you'll notice it's not sitting here. It didn't stop. So actually, it would be like right here. So what we do, and the reason I've done all this scribbling, is that when you draw it, you're going to have a dot, 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 and then this other dot is going to be magically have basically moved back, start going the other way. So what we do to show that is we just draw a diagonal arrow. Okay? So if you have a situation where an object turns around without stopping, the motion map is going to look something like this. All right? Where instead of having a dot stacked on top of each other, the next dot is going to be at its position. All right? So, question 4 looks pretty good. Let's start with the last part. Question 5. So for question 5, this one was a little tricky because it did not give you anything except a motion map. And actually, this motion map is a little misleading because I told you how you want to connect the arrows. Well, unfortunately, they did not listen to the rules. They did not connect the arrows. So actually, in case you're staring at it kind of confused, these arrows should be going all the way. All right? But even without that, you can kind of clearly see there are 2 distinct motions going on here. All right? So once again, it really doesn't matter which one you pick. It's whichever one you're most confident with. I'm going to start with the written description. So remember, we start with the starting point. So looking at this motion map, the starting point is right here. Okay, so I'm just going to say starting, and because I can look at this graph, if you want to, you could literally say it starting at -5 meters. If you want, you could just say starting at a negative position. But either way, I'm going to say just starting at -5 meters, the object moves with a constant positive velocity, because it does. You'll notice in the first section, it's moving with a constant positive velocity. All right. And then what happens is that you notice the arrows get shorter. The dots get closer together. So what we're seeing is that right now this is moving pretty quickly. And then once it crosses the origin, it's about 1 meter, it starts to slow down and move. It slows down. All right. And what happens is now it's just moving at a slower constant positive velocity. All right. So what happens is it looks like this. So you can say when it crosses the origin, it's really up to you how you want to change it. But the object starts at a negative position and moves at constant speed or constant velocity in the positive direction. When it crosses the origin, it continues in the positive direction at a lower constant velocity. All right, remember once again, I'm going to include this. You have to include that word constant because it is very important. All right. Now, if we look at our 2 graphs, the position time graph, it's going to have 2 things to represent kind of the different velocities. All right. Starts with a negative position, and that's exactly what we have in this graph right here. It's on the negative side. It has a constant positive velocity, so it's going nice and linear. And then, to signify that now it's going with a constant positive velocity but slower, we have to decrease the steepness. This has to be less steep now to make it work. All right? So right there we have 2 distinct motions. Fast constant positive velocity, slower constant positive velocity. All right? And once again, the steepness of that slope tells you how fast you're moving. And then, of course, just like we talked about before, the velocity time graph, we look at each section. Because this is constant positive velocity, we just need a horizontal line that signifies positive velocity, so it's on the positive side, and it needs to be higher up than the second section because it's moving faster, which is why this section is now a little bit lower because the velocity is less. Okay? So, I know we just went through a lot of information here. All right, and once again, we're going to keep practicing this. I'll put the link to this PhET activity. It will not work on your Chromebooks, unfortunately, but if you have a desktop or laptop that isn't a Chromebook, you should be able to play around with it. This is a really useful tool for drawing these position time graphs and kind of, seeing how you can affect the motion of an object. All right. So, with that being said, Once again, just like always, if you have any questions, shoot me an email. Come to virtual office hours. Talk to me in class if you can do that as well. It's really up to you. Otherwise, have a great rest of the day, and I'll talk to you later.